This video is going to be about resistors and circuits. Okay, so they're going to be purely resistor circuits. And resistors are different from capacitors in that capacitors are energy storing devices, whereas resistors are energy dissipating devices. Okay, so resistors absorb the energy from some sort of a source, and then they re-emit it in some other form. Okay, so it can be in the form of light or heat. So for example, a light bulb is a type of resistor. Okay, so the relationship between voltage and current in a circuit that only has resistors in it is directly proportional. Okay, and the resistance is the constant of proportionality between the current and the voltage. Okay, so V equals IR is a relationship, and it's called Ohm's law. Okay, so this is Ohm's law. So suppose you have a circuit that has a voltage source V and some resistance R. Okay, so then what's going to happen is this voltage is going to cause a current in the circuit that's going to flow clockwise. Okay, this is going to be the current, and current is going to equal V divided by R. Okay, so this is the voltage of the battery, and the voltage across this resistor is going to be the voltage of the battery also, because all of it has to fall. Okay, and then this is going to be the current in the circuit. Okay, so now what if you had a circuit that had two resistors in it? Okay, so it's a series circuit and you have two resistors in it. Then now what is going to be the voltage and the current across the, or current in the circuit? So we know that current is going to flow like this. Okay, and then we know since this is a series circuit, the voltage is going to fall across the elements. Okay, and then the voltage drop, once you sum it all up across all the elements, then it should add up to the voltage of the battery. Okay, so if the voltage across R1 is V1, and if the voltage across R2 is V2, then the voltage of the battery source should equal voltage across R1 and plus voltage across R2. Okay, and here's your current. Then since this is a series circuit, okay, then current is the same everywhere in a series circuit. Okay, so current is the same. Okay, so then we can get the circuit in another equivalent form. Okay, very similar to what we had done with the capacitors. Okay, so where this is, some equivalent R, and then this is your simplified circuit. Okay, so then this is going to have some current I going through it, and this I is going to be the same as the current in this circuit, because this is a series circuit simplified over here. So V of the battery is equal to I divided by, or I times R equivalent, okay, which is this, equals, and V1 is I times R1, and V2 is I times R2. Okay, so currents cancel. So total resistance or equivalent resistance in a series circuit is just the sum of all the resistances that you have in a circuit. Okay, so you can simply add up all the resistances that you have, and find your current and your voltages based on the current that you find. Okay, so resistors in a series circuit are very straightforward. Alright, so now let's look at resistors in parallel. So let's say you have two resistances, R1 and R2, and they're connected in parallel across the battery. Okay, so now how do you know that these two components are in parallel? Okay, is it because they're parallel, they're drawn parallel to each other? Is that why? Well, okay, but they don't have to be drawn parallel like this. So even if you had drawn the circuit like this, for example, we had R1 here and R2 like this, then they're still in parallel. Okay, so what determines when two elements are in parallel? It is determined by whether or not they share their beginning points and their ending points. Okay, so R1 and R2 have the same beginning point. Okay, so this wire doesn't really matter. Okay, wire doesn't matter in these circuits. Okay, and then they also share the same end points because the wire doesn't matter. So whether it's drawn like this or like this, you can see that that beginning point of these two resistors is the same, and so is the ending point, because this wire in the middle doesn't matter. So that's why they're in parallel. In series circuit, that's not the case. Okay, in series circuit, it's like this. Okay, so here's the beginning point of this circuit, this resistor, and here's the end point, and here's the beginning point of this resistor, and here's the end point. So so these two are sharing their beginning and end point, but these points are different. So this one is in series. Okay, and here the battery is also in parallel with these two resistances. Okay, because this is the beginning point and the wire doesn't matter, and this is the end point. Okay, so all these points are the same points, and all these points are the same points. Okay, more formally they're called nodes. Okay, so this is the same node, and this is all the same nodes. So when two components are sharing a node, then they're in parallel. Okay, so in a parallel circuit, the voltage is the same everywhere. Okay, but what happens to the current is the battery sends out some current in this direction, I, and then this current divides in two. Okay, so it becomes I1 here, and it becomes I2 here. Okay, so this current came in here and divided into two parts, I1 and I2. So I is equal to I1 plus I2. Okay, and V is the same everywhere. V is the same in both branches, or in branches that are in parallel with each other. Okay, so then you can redraw this circuit as a circuit with a single equivalent resistance. Okay, so this is your V, this is your equivalent resistance, and this is some current going through it. Okay, now this current that's going through this R equivalent is the current that the battery is producing. Okay, so you simplified these two R's into a single one, and what you're left with is this current. Okay, so this current is equal to V divided by R equivalent. Okay, and I1 is equal to the voltage across R1 divided by R1. So voltage across R1 is V, and voltage across R2 is the same as voltage across R1, which is V. So it becomes V over R2, so V's cancel. So R equivalent in parallel circuits is the way you find the equivalent capacitance for capacitors in series. So series and parallel circuits are sort of opposites of each other when it comes to finding the equivalent capacitance or resistance with circuits with resistance and capacitance. Okay, so that's parallel circuits, simple parallel circuits. Okay, you need to know these three things: that current divides in the branches, and voltage is the same in the branch, and this is how you find the equivalent resistance. Okay, in series circuit, you need to know three things also: that voltage drops across the components, and current is the same everywhere in the series circuit, and the R equivalent is the sum of all the resistances. Okay, now let's do a problem that is slightly more complicated. So suppose you have a battery here and some resistance R1 here, some R2 here, R3, and R4. Okay, so this is the same circuit that we had in the previous video with capacitors, except now we have this with the resistance. Okay, so we're gonna use the same strategy that we had in the last video. We're gonna start simplifying it from the end, and we're gonna work inwards. And then, to find the currents and the voltage drops across each of these resistors, we're gonna work backwards. Okay, so first of all, you can see that R3 and R4 are in series together, right? Because here's the beginning point of R3, and here's the end point. Here's the beginning point of R4, here's the end point. So they're not sharing their beginning and end points, so they're in series. Okay, so then this one you can simplify into a single R, and it's easy to just add these, so it's R3 plus R4 here, or you can call it some R equivalent. Okay, and then you see that R2 and R3 plus R4 are in parallel together. Okay, so this is R1. So this is so to find this, you can say that this R equivalent. Well, let's do the same thing. So this is, let's call it R equivalent 2, and let's call it R equivalent 1, is equal to 1 over R2 plus 1 over R3 plus R4. Okay, so then in this circuit, you can find out the current here. Okay, so the current is going to be V over R1 plus REQ2. Okay, so then once you find this current, then you can find the voltage across R1. Okay, voltage across R1 is going to be I times R1. Okay, so that means we found the current in R1 and the voltage across R1, so we're done with R1. Okay, and then we know the current and this equivalent resistance, and from that we can find the voltage. Okay, so voltage across this is going to be I times the resistance, okay, which is REQ2. Okay, so then this voltage is these two resistors simplified, so that means this is the voltage across this branch. Okay, so voltage across, voltage at this point, at this node. So remember, this is the same node because the wire doesn't matter. VREQ2 is the voltage here. So that means that the current in R2 is going to be IR2 is going to be VREQ2 divided by R2. Okay, and so that takes care of R2. We found the current in R2, and this is the voltage across R2. Okay, and then what about this one? So then we know that the voltage is this, so we can find the current. So current in this branch is going to be R equivalent, one branch is going to be VREQ2 divided by REQ1. Okay, so this voltage divided by this resistance is going to give you the current that's going in this branch. Okay, so once we know the current that's going in this branch, then this is the same current that's going through R3 and R4. Okay, because we just simplified R3 and R4 into one. It's still the same current. Okay, so then once we know the current in R3, then we can find out the voltage across R3. The voltage across R3 is going to be V3 is equal to IR EQ1 times R3. Okay, and then voltage across R4 is going to be IR EQ1 times R4. Okay, so that's how you'd find the voltage and the currents across the these resistors. Okay, and one thing you could have done was, you could have taken it one more step over here, and you could have simplified this into a single resistor, and then worked backwards. You could have found the current here, and then said that, okay, so then since this resistor is these two simplified together, and these were in series, so then this current is going to be the current through each one of these also. Okay, and so that would have been the same thing. Okay, so that's that takes care of this example. Let's talk about Kirchoff's laws. Okay, so there are two of them. One is Kirchoff's voltage law, and one is called Kirchoff's current law. Okay, so Kirchoff's voltage law says that sum of the voltages around the loop is equal to 0. Okay, and Kirchoff's current law says that sum of currents into a node is equal to 0. Okay, so for example, so we've already seen this before, right? So we saw that we had that circuit. This is the simplest example of Kirchoff's voltage law. This is the voltage of the battery. And this is some resistance in the circuit. Then if suppose you start at any point and you make a full round trip, okay, you make a full loop, then the voltage, some of the voltages, okay, whether it's a source or whether it's an energy absorbing device like a resistor, then the voltages are going to end up being equal to 0. Okay, so for this case, you're going to go from here to here, and you're going to gain a voltage of V because your battery is providing some voltage. And then in going from this point across R, you're going to lose voltage. Okay, and then that's it, because this wire doesn't matter. So some of the voltages is going to end up being equal to 0. Okay, and that's because the current is flowing like this. So whenever you're going in the same direction as the current, then your voltage drops. Okay, so that's why there's a minus sign here and a plus sign here. Okay, if you like the opposite sign convention, that's fine. You can use that. So this here implies that the voltage across the resistor is the voltage of the battery. Okay, suppose you had two resistors. Okay, so current is going in this direction, R1, R2. Then you start at this point and you go from here to here, and you gain a voltage V. Okay, then you go from here to across R1 and you lose some voltage, R1, and then you go from R1 to R2 and you lose some other voltage, R2, and that's equal to 0. Okay, so this is saying that voltage across R1 plus voltage across R2 has to equal the voltage across voltage of the battery. Okay, and this makes sense because that's what we said earlier for series circuits, that the sum of the voltages across the components has to equal the voltage of the battery. Okay, so this is Kirchoff's voltage law. So one more note. Suppose that you have a resistor here and a voltage here, and you for some reason say that, oh well, let's just say the current is going in this direction. Okay, then you would write your Kirchoff's voltage law like this. You would go from here to here, and you gain a voltage V, and then in going across the R, since you're going against the current, you're gonna add the voltage across R. Okay, it becomes a positive, equal to 0. Okay, so then this is the current. Then VR is what? VR is current times the resistance. So V plus IR equals 0. So it implies that I equals negative V over R. Okay, so negative current means that it doesn't mean that your answer is wrong. It just means that the direction that you had assumed that the current was going in is wrong. The current should be going in the opposite direction. Okay, so when you're doing these problems and you end up getting a negative answer, just then don't change anything. It just means that the direction of the current is opposite from the one that you assumed. Okay, so this is the correct direction of the current, and this is wrong, but then your answer told you that this was wrong, so you're fine. Okay, so for Kirchoff's current law, for example, you know that suppose you had a circuit like this, then there's some current going here, and then what happens is this current is going to divide into I1 and I2. Okay, so Kirchoff's current law is saying that I is equal to I1 plus I2. Okay, so so this would be one example of how you would apply Kirchoff's voltage law. Current law. Basically, it tells you that how the current is splitting in different branches. Okay, so let's do an example. So suppose you have a circuit that looks like this. Okay, suppose this is R1, R2, R3, R4, and R5. Suppose this is V1, this is V2, and this is V3. Okay, so now suppose you have to find the current and the voltage across all these resistors. Then how do you go about doing that? Okay, so these are neither in parallel nor in series. Okay, so here you have to apply Kirchoff's laws. So with Kirchoff's law, what you do is you assume a direction of current in each loop, and then you apply your Kirchoff's law based on that. So so let's assume that in this branch there's some current going in this direction, I1, and in this branch, let's just say there's some current going in this direction, I2, and in this branch there's some current going in this direction, I3. Okay, so then so let's first do Kirchoff's voltage law in the upper loop. Okay, so let's start at this point. So we're gonna go from here to here, and we're gonna gain a voltage of V1. Okay, and then we're gonna go from here to here, and we're gonna have a voltage drop of I1 times R2 minus I1 R3. Okay, so from here to here is the same branch. Okay, and from here to here is the same branch. Okay, and then this third one is its own branch. Okay, so minus I1 R3, and then we continue on, and then we go across from here to across V2, so we gain another V2, and then plus I2 R1 equals 0. Okay, it's plus because we're going in the direction that is opposite to I2. Okay, so we completed a loop like this. Okay, so now let's do the same thing for the bottom loop. Okay, let's start at this point. So we're gonna have negative I2 R1 and then minus V2, right? Because we're going from plus to minus of the battery. And then now we're going against the current across R4. So it's going to be plus I3 R4, and then go across a battery. Then it's going to be minus V3 and plus I3 R5 equal to 0. Okay, so since you have two loops in this circuit, you can only have two independent loop equations. Okay, if you want, you can write another equation for this big loop. Okay, but what you're gonna find is, that if you add these two equations, you're gonna end up the equation that you would get if you were to write this equation. Okay, so we can do that. So suppose you started out here, and you're gonna make your full circle. So you're gonna say minus I3 R5, okay, plus V1 minus I1 R2 minus I1 R3 minus or plus I3 R4 minus V3 equals 0. Okay, and then you'll see that actually this one should be plus. Okay, because we were going in the direction that's opposite to the current. Okay, so then you will see that if you add these two equations, then let's see. So let's see, I1 R2. So we have this term here, I1 R3. So V2 goes away. And what else goes away? And then this term goes away. So how many do we have here? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. So basically, if you add these two terms or these two equations, then you're going to end up getting this equation. So it's not really telling anything new. So, you can get this equation or not get this equation. Or you can, get this one instead of getting one of these loop equations. And, that's all you would need. Okay, then third equation you need is the current equation. So you can, there are many ways to do it. So basically what's happening is I1 is coming here, I2 is coming here. So you can say that I1 plus I2 is equal to negative I3. Okay, so you're saying that I1 and I2 end up becoming I3. And since we drew I3 like this, going in this direction, then you have to change the sign of I3. Or you could have also said that I3 plus I2 end up making negative I1. I3 plus I2 equals negative I1. And which is you could have manipulated this one algebraically, and you could have gotten this one. Or you could have looked at the picture and derived it. So so that's how you approach Kirchoff's law problems. So when a lot of the times when you have multiple branches, multiple voltage sources, you end up having to use Kirchoff's voltage law. And then after you get to this point, it's algebra. Okay, so basically this is going to be at most a 3-equation and 3 unknown problem. Anything more, then the system cannot be solved. Okay, so that's how you approach Kirchoff's voltage law problems. Okay, so now that we've discussed resistors in a circuit, let's get back to how a resistance is defined. So resistance is defined as the resistivity of the material times length over the area. Okay, so area is the cross-sectional area, and length is the length of the current carrying wire, and this is the length that's along the direction of the current. Okay, so for example, that if you have a wire that's carrying current in this direction, and it's so long, its length is L, its cross-sectional area is A. Okay, then you're gonna plug in these parameters over here, and resistivity is a constant, and then you're gonna get the resistance for the material. Okay, so suppose that if your current is flowing in this direction, then that's fine, right? Everything is easy. But if you have the case where you have a cylinder, and you have let's say another cylinder here, and your current is flowing in this direction. Okay, then what do? Then what's happening is, so suppose that this is R1, the inner R, and the outer R is R2. Then what's happening is, as you go farther away from the axis of the cylinder, your radius is increasing. Okay, so your radius is changing. So to find the resistance, it's not just rho L over A. What you have to do is you say that R is equal to rho. Rho is still a constant, and area is 2 pi R L. Okay, so L is here, this, but this is not this L. Okay, because this is L is the direction that the current is flowing in. So L, and then this becomes, so L is, is actually the radial direction that the current is flowing in. Okay, so it's going to be integral from R1 to R2. So that's how you set this. Okay, so remember, this L is not this L. Okay, so this L in this problem is dr, because the current is flowing radially away. And because your resistance is changing, you have to integrate to find the resistance of this material. Okay, so resistance depends on the direction that the current is flowing in. Okay, real quickly, we can also define the current. So current is defined as delta Q over delta T. So what it means is that, suppose you have a wire and, electrons are flowing through it, then how much charge flows through the cross section of the wire in a given amount of time. Okay, so that's what current means. Another way you can write current is, suppose you define the density of the charge and say that the charge per unit volume is the number of electrons times the charge. Number density. So if you multiply the number of electrons times the charge of an electron, then you get the total charge. And then little n is the number of electrons divided by the volume. Okay, so if you multiply the volume by area times the length of the wire, then you get the Q, right? Because what you're doing is you're basically dividing it by the volume, but then you're multiplying it by the volume also. Okay, so this is the amount of wire, so this is delta L. Okay, and then over delta T. So this part is delta Q over delta T. Okay, so then this you can also rewrite as NEA times the drift velocity of the electrons. Okay, so remember, so this is the number of electrons per unit volume. This is the charge of an electron. This is the cross-sectional area. This is the drift velocity. Okay, so drift velocity is, so current is not the velocity of the charges. Okay, so because charges, they, move around in some weird fashion inside the wire. They even go back. They go forward. They go upward. Okay, so this is what the drift velocity of an electron looks like. Okay, it goes in all different directions, but the current as a whole moves forward, and this is how current is defined. It's the total charge divided by the total time. Okay, so one final comment about current. Okay, so what makes the current flow? Okay, so we saw that, suppose you have a wire connected to a battery. Okay, and let's zoom into the wire and blow it up a little bit. Or in fact, just let's assume that this here is a conducting cylinder that is directly connected to the positive terminal of the battery, and this is a conducting cylinder that is connected to the negative terminal of the battery. Okay, so suppose it's like this, and it's like this. Okay, and it ends over here. Okay, so now, now this is a conductor, and there's a lot of positive charge on the positive terminal of the battery. There's negative charge on the negative terminal of the battery. Okay, so what is that going to do? This positive charge is going to be start flowing on the conductor, and where is it going to go? Okay, it's going to go to the conductor, and then once it reaches equilibrium, the charge is all going to be on the outside of the conductor. Okay, and similarly down here, all the charge is going to be on the surface of the cylinder. Okay, once it reaches equilibrium. But what happens if you connect these? Okay, so you took these and you connected them together. Okay, so then what happens is, the positive charges that are on this one and the negative charges on this one, they start canceling each other. Okay, and once they start getting canceled, more positive charges come over to take their place. Okay, and similarly, more negative charges come here to take its place. Okay, so these charges start moving. And what ends up happening is, so basically, you have positives here, negatives here, and then you have more negatives here and even more negatives here and very negative here because it's right next to the terminal. Okay, and so same thing here. You have more positive here, more positive here, more positive here. Okay, and most positive right next to the battery terminal. Okay, and then what this gradient of charges does is it establishes an electric field inside a conductor. Okay, so if you have a charge, say, then these positive charges are going to be pushing it in that direction. Okay, and these positive charges are the charge reduces, so so these are also going to be pulling this charge backwards, but all in all it moves in this direction. Okay, and then similarly here, once the charges over here are being pushed by these positive charges and they're being attracted by these negative charges, and so that's what makes the charges inside the wires move. Okay, it's this gradient that is set up on the surface of the wires. Okay, so a single charge may only move very little bit for in a very long time, but it can maybe let's say it only goes from here to here. But current as a whole is moving clockwise, and that's because there's this gradient of charges, and it's affecting every point of the wire. Okay, so it's not like that. It's not that this charge has to travel all the way from the positive to the negative. In that formula that you had for current, it's not that so much charge has to travel from this end to this end, and so in this amount of time to constitute so much current. It's just that they're all moving together at the same time. Okay, and the collective motion of the charges constitutes current. Okay, so I hope that's clear. Just wanted to make this comment. Just clears up a conceptual idea. So that's it for circuits with resistors. If you have any questions, please leave a comment.